Hello boys, I'm going to take you through the theory for exercise 6E, do a bit of background, a bit of revision, and a bit of theory to help you do the graphs in 6E, which is graphing cubic functions that are in the point of inflection form. The point of inflection form. Just want to compare that to quadratics and the turning point form. You'll remember the basic formula for quadratic and turning point form. X minus h squared plus k gives you a turning point of hk. Well, for a cubic, it works the same way. It's the same format. X minus h cubed plus k has a stationary point of inflection, or an SPOI, or a SPOI, at the point h and k. The basic cubic is graphed here. This is y equals x cubed. It's the basic shape of the cubic. You'll see right here at the origin, at the point 0, 0, is what's called a SPOI, or a stationary point of inflection. Right at that point, the graph is perfectly flat. Before it, it's got a positive gradient. After it, it's got a positive gradient. But right there, it's got a zero gradient. There's a couple of other key points I want to point out to you. X is 1, Y is 1. If you cube 1, you get 1. X is minus 1, Y is minus 1. If you cube a negative 1, you get negative 1. It's just good to remember that those 2 points exist. When you draw a cubic, if it does go through the origin, you always need to show another point to indicate scale. That 1, 1 point is obviously a good one to indicate. The domain, or implied domain, of a cubic is all real numbers. There's no restrictions, there's no fractions or square roots to restrict the values of x you can put into the function. The domain is R, the range is also R. On the right hand side is a graph showing you the comparison of an x squared versus an x cubed. They intersect at the point 1, 1. Underneath 1, lower than 1 for x values that are fractions. X squared graph will be higher. A half squared is only a quarter, whereas a half cubed, if we're just here at a half squared is a quarter, but a half cubed is an eighth. It's lower. But as soon as you get above 1, x cubed shoots away quickly. For example, at the point 2, 2 squared is 4, but 2 cubed is 8. And so we're right up there somewhere. For that parabola, I've listed the domain and range to compare as well. Domain is reals, but the range is just the positives, because when we square the negative numbers over here, it becomes positive. I think you should pause the video now and take down some notes from that general introduction: the basic shape of an x cubed, the stationary point of inflection form, perhaps the comparison to the x squared graph, the domain and range. Pause the video, take a few minutes to take that down. I'll assume you've paused the video and taken some notes from that first section. So now we're going to look at dilations, reflections and translations, or Dr. T. We always do our graphs transformations in that order: dilations first, reflections second, and translations third. This screen has got some dilations. I'll quickly take it through you. You can pause the video and take some notes. If we put a number in front of the x cubed, like an a, that's like putting an a in front of the whole function, we are dilating those y values. A is a dilation factor from the x-axis, or in the y direction, and there I've drawn 3. The basic x cubed in black in the middle, 2x cubed, which has been stretched up to, you can see it's been stretched up to, and a half x cubed, which has been stretched down a half. All points have gone up 2 to get to the blue graph, or down a half, by a factor of a half to get to the green graph. Pause the graph, pause the video please, and take down some notes that you need on dilations. These are dilations where the dilation factor is in front of the function, a times the function. I'll let you pause the graph. Pause the video. Okay, presume you've paused the video, taken the notes you need. Let's quickly look at reflections. Again, we've got our basic x cubed graph here in black. If we put a negative in front of the whole function, like negative function x, we are changing all the y's from plus to minus. We're reflecting in the x-axis from positive down to negative, or vice versa. You can see here I've drawn in blue the negative x cubed graph, and it has been reflected in the x-axis. From top to bottom, from bottom to top. Over on the right hand side of the screen, we have put the negative inside the function. When we put a negative inside the function, we're changing the values of the x from plus to minus. We're reflecting in the y-axis. You'll note that when I take this x cubed graph in black and reflect it in the y-axis, I end up with the same shape as if I reflected in the x-axis. The green graph and the blue graph are the same. That's because if I put negative x inside the bracket here and cube it, negative x cubed is negative x cubed, which is the same as what we had over this side. Those functions, by the way, are called odd functions. You'll do that. We may have done it already, or you'll do it at another point, where the reflection in front of the function and the reflection inside the function, the reflection in the x-axis and the reflection in the y-axis give you the same graph. That's called an odd function. Pause the video, take some notes on the reflections, please. Assume you've paused the video and taken your notes on the reflections. So I'll move on to the last section, and that is translations using the translation form x minus h cubed plus k. The h is a horizontal translation opposite to the sign in the bracket. Every one of the functions you do works that way. Opposite to the sign in the bracket for the parabola, opposite to the sign in the square root, opposite to the sign under the fraction for a hyperbola or a truncus, opposite to the sign in the bracket for the circle. We always move opposite to the sign inside. It's a horizontal translation opposite to the sign. The k at the end is a vertical translation in the same direction. Vertical translation in the same direction. Here are two simple examples. First example, x squared plus 3, a vertical translation of plus 3. So we move our stationary point of inflection up 3 to 0, 3. That was easy to get. If I then drew it in blue, you'll see that I'm missing here an x-intercept. So we calculate the x-intercept as all as normal, let y equals 0, and we get 0 equals x squared plus 3, just a little rearrangement, x squared equals minus 3. Oh, that's a cube, I'm sorry. X cubed equals minus 3. So x equals the cubed root of minus 3. Yes, there is a cubed root of a negative number. It's in fact a negative. And so we then have a x-intercept of cubed root minus 3, comma 0. We label our graph with our x and y intercept with our in our coordinate form, xy coordinate form. Cube root minus 3. Here's another one. Y equals x minus 2 cubed. The horizontal translation opposite to the sign in the bracket. We're moving plus 2. So the stationary point of inflections come across 2. We've labelled that. I've drawn it in, and clearly I'm missing a y-intercept. Let x equal 0. Y equals 0 minus 2 cubed. Too easy. Minus 2 cubed is minus 8. 0 minus 8 is, of course, that y-intercept. So very simple vertical and horizontal translation. Finally, pause the video if you wish and take down those notes. Presume you've paused and started again. Here is the last example for today. Y equals 2 times x plus 1 cubed minus 3. It's good to get into the habit of writing down what all the transformations are. The first transformation in Dr. T order, DRT order, the first translation, there's a dilation times 2 in the y direction. That's a stretch up times 2. Second translation is a horizontal translation of negative 1, opposite to the sign in the bracket. And the third translation is a vertical translation of minus 3, the same as the sign. So there are three transformations. Essentially, when I graph it, I actually don't do it in Dr. T order. When I put it onto the graph, I do the translations first. So I'm going across 1 and down 3. So I'm going to mark my stationary point of inflection there. I know the basic shape. It's a positive cubic, so it's shaped like that. So I'm going to put this bit in here. I can safely do that. And then I have to think, well, it's going to go up there somewhere. I'm going to need to get the x and y intercept, so I'll do that next. For the x-intercept of y equals 0. 0 equals 2 brackets x plus 1 cubed, take 3. Add the 3 over and divide by the 2. I just like to write it around the other way usually. Cube root to both sides, cube root both sides, cube root of 3 on 2, subtract the 1. X equals the cube root of 3 on 2, subtract 1. You should write that in an ordered pair. You could put the minus 1 in front of that square root. Probably some people would do that. Comma naught, either way. And then for the y-intercept, x equals 0, so y equals 2 brackets 0 plus 1 cubed minus 3. Y equals 2 times 1 cubed minus 3, that's 2 minus 3, y equals minus 1. We have a point 0 minus 1. We've got 0 minus 1 there, something in there. As long as I'm showing, when I draw this, that that's pretty flat there, I'm labelling 0 minus 1. I could do a better graph than that, but anyway. And then you need to label this point here. So, cubed root 3 on 2 minus 1 comma 0. You can, that's the end of our notes, of quite a lot of notes there on graphing cubics in the point of inflection form. So you can now pause the video if you like and take down those notes. And I'll do another little video for the very last couple of questions in the exercise as well.